Hello, everyone. Hello, Frank.
Hi,
How's it
Denis.
going?
Good, good.
Look- Yeah, looks like you decided to share the screen from scratch. Have you prepared something special? I see your screen sharing. If you want to hide it right
Sorry,
now,
I
you
have
can.
to remove that. Yeah.
Yeah, because that was. But that's a good reminder that today we are going to do a lot of hands-on exercises, and folks, Frank is ready. So, hello to all of you who are joining us today from wherever you are, and hello everyone to those who will be watching us later on demand. So today, neither I nor Frank are at our home offices. We are traveling. The conference season is coming to an end. How about you, Frank? Where are you these days? What's the country? What's the conference?
It's UK UEG, an Oracle user group conference where I was talking about Linux in general. And yeah, it was nice, except it was kind of fun because the Wi-Fi doesn't work. The cloud where I had my demo didn't work. The screens didn't work at the beginning. But yeah, we finally made it. And we also did it interactive with whiteboard. And yeah.
Can you actually show a picture of that whiteboard because you tweeted right that a few hours
Uh,
ago. I just want the folks to see how like you finished the presentation because when you live in this high tech world, usually you at least trust Wi-Fi. If Wi-Fi doesn't work, then at least you expect the screen sharing would be working right, the projector. But in your case, everything went down. That was a total collapse. But you found a way. Just show
Yeah,
the
let me
picture of the whiteboard.
check. I should have that on Twitter because those are really the kind of thing that I tweet, but I cannot find it right now. But at least we had a whiteboard.
Never
Yeah,
mind.
let me
Never mind.
share the screen and you will see it. Just checking for the button. Yeah,
Okay,
here it
that's
is.
great.
Yeah. So yeah, at least it was in an office where they did some training. So at least we had whiteboards. That's not common today, and I think we should have that in all rooms in all conferences because when there are discussions, sometimes it's kind of interesting to show that. And that was about Linux and the process state running and disk and all that. So yeah.
Excellent. You know, it reminded me when I saw this whiteboard picture. It reminded me of my days at college. That's how we learned. Also, like we had professors. We certainly had those big, not laptops, but we had those PCs, standing PCs, boxes when we
Yeah.
learned programming and all the computer science stuff. But still, a whiteboard was one of the primary way of communication between a professor and students, and that's what like jumped back for me in the past.
But also when you discuss a topic, it's very useful in the discussion to discuss around the whiteboard, and we miss that. Of course, remotely it's more difficult, but I remember some great discussions with product managers or yeah, when you talk about architecture, and it's always easier to show how things
Mm-hmm.
communicate. And at the
Mm-hmm.
end, you take a picture of the whiteboard, and then you have something to remember. Yeah.
Exactly,
And
exactly.
you,
It's
where
not
are
that.
you?
So I'm in San Francisco Bay Area. Uh, I joined the conference called Scale by the Bay. It took place. It's still today the second day, and I'm planning to go there. My presentation was yesterday about scalable, low latency, multi-region applications, and it's not a surprise that I used also YugabyteDB as a database. So that's a wonderful conference. The first day was full of topics on AI, ML, machine learning, text to SQL generation. That's very hot, especially in the Bay Area, San Francisco, because there's so many startups in here, like from those companies
Yeah.
like you have certainly Google, Apples, etc. of the world here, but also many startup companies who are building real cool stuff using AI, OpenAI, and other models. So like the first day was all about AI plus cloud. Still, you need to have cloud if you want to build scalable UI AI. You need to have cloud, and that's
Yeah,
also
because you
resonates
need a
very well.
lot of resources and you probably need elastic resources. Yeah.
And that's why I think that I briefly yesterday I watched a quick recording of the OpenAI Devs Day. So like OpenAI, that company that created ChatGPT, folks, if you don't know what OpenAI is, like you know certainly ChatGPT, and ChatGPT was created by OpenAI, and ChatGPT you can chat to it, right, asking all those questions, but also you can use its APIs as a developer, as a programmer. And yes, and they had a couple of days back their first conference, and they kind of announced, like there were many good announcements. Eventually, and then Satya Nadella, the CEO of Microsoft, went on stage, and they actually talked about this partnership collaboration. So like the success of OpenAI also depends on their Microsoft's resources, because they run everything in Azure, and Azure is very scalable. Azure was being prepared for that AI, let's say, wave, AI transformation, and that's why. And I can, even as a user, I can see this scalability and performance improvements, because ChatGPT models are becoming more faster, less delays, no any restrictions, etc.
Mhm.
Okay, so let's do this. Let's jump. As for the highlights, yeah, in the end, of the time left, I will talk about Cone Gateway, because a few weeks ago uh, we supported some of the DDL commands, and that made possible to use Cone Gateway, Cone Mesh on YugabyteDB. There is a detailed article that might be interesting for some of you folks who are building microservices and API gateways. But now let's switch to our primary topic for today. And folks, don't hesitate to ask questions. We always will pause and answer whatever you want to learn from us. But Frank, handing over to you. What have you prepared for us today?
Probably the feature that I find the most interesting. I spend a lot of time looking at execution plans to understand how the things works, to look at the improvement we do in the access path and the join method and the cost estimation, all that, and also to help users with their query, and help customers also with their query. So the more I can see from the explain plan, and the more happy I am. And we have added many metrics in explain plan, in the explain analyze, and then I think it's quite interesting to look at them, to be sure which kind of metrics we can get, but also about their meaning. The problems with performance metrics and instrumentation, usually they have a name that is more related to the architecture, and we need to understand what it really measures.
Mm-hmm. So let me digest. Let me digest what you have just said. So explain, analyze. We already have this explain statement that is supported by Postgres, right? Query layer, and we reuse Postgres query layer. And when you run explain with any parameters like analyze, buffers, costs of, etc., we are just using the Postgres source code, and Postgres shows us what's implemented in the Postgres layer. But at the same time, then those queries are executed over our distributed storage layer, DuckDB. And what you are going to show is the storage level metrics that were added to the explain statement of Postgres. Right?
Maybe I will start to show a bit of our architecture. Basically, when we connect with the application, we connect to a Postgres backend. It's a fork of Postgres. There is some code that is different, but basically it's like a Postgres backend. And the SQL part, so parsing the query, building the execution plan, and running through the execution plan, is kind of Postgres code. So what we see from there is very similar to Postgres. But where Postgres reads and writes to the shared buffer and then to the disk, this is where we do something different. We have a stateless layer for SQL, and all reads and writes go to the network. Read from the tablets with remote calls to the different shards, tablets for the tables and indexes, and there are RocksDB LSM trees, which means that if we want metrics about the execution, we need some things from the SQL layer, and those just come from Postgres. But we need more metrics that comes back, means that when we do remote calls, we get the result plus additional metrics that can tell what has been done, how many reads, and give an idea of the complexity, the cost of the queries.
And also,
So
could you stay just for one extra minute on this picture? I just want to highlight to some of the folks, because that also was a surprise for me in the past. When we keep saying that we reuse PostgreSQL source code, and that when application connects to that SQL layer, you connect to the Postgres backend. And under this Postgres backend, we literally mean the PostgreSQL process. So folks, if you start a YugabyteDB node on your laptop using YugabyteD tool, then what Franck shows here as the SQL layer, that's a Postgres process. You literally will see Postgres process running in your operating system. It's Postgres. It's our version of Postgres that runs, and that version of Postgres has some modifications in the query layer so that Postgres can talk to our storage. So that was a big surprise for me in the past, because I was thinking, oh, I would see in my operating system some YugabyteDB specific process for the query layer, for the SQL layer, but no, that was Postgres, literally Postgres process.
yeah, and it's also a kind of challenge. We want to be Postgres compatible, so the more it looks like Postgres, the better it is. But we also need to add some information about the what is distributed. So the execution plan is a mix of both, and must be easy to understand by Postgres users, but with additional information. And I've started a Docker container with the latest version, latest preview version that is available. So it's just the latest image from it.
Mm-hmm.
And let me just create a sample table here and add some rows. I don't know how. Okay.
So you're adding 1 million rows. Yeah. Oh, no. Okay.
No, just let me create the right table, because I did some tests before with an additional column. And we'll see how long it takes here. I wanted to do the demo on the clouds, but I have kind of bad Wi-Fi, and that I didn't want to overload the streaming with that in addition. So I started a Docker container. We'll see how long it takes.
How many nodes do you have in your YugabyteDB cluster?
No, that's only one node, one container that I started. Let me show. I use quite often when I run something on my laptop. I use Docker Desktop, which is very nice. It has more and more feature. You can see the CPU consumption, for example, for it. And I just started Yugabyte in it. And maybe I will create a table that is smaller if it takes too much time. We will see. In the meantime, what I will do maybe is...
That's okay. Yeah, let's give it some time, Eugene. Yeah.
I will just connect to it Docker PS from another terminal. But of course, it uses a lot of CPU.
Looks like we came across some surprising situation. It's generating 1 million series. Yeah, it looks like something gets stuck in the container.
Maybe it was not a good idea to do that on Docker. I will cancel that, and we will do it again. The problem is the environment that I had on the cloud has kind of problems. Okay, I think I will just...
For me, the Docker, like I use macOS, and for me, the Docker, it works 100% of the time on Docker, but not always the fastest way possible, because like on Mac, it's like, for some reason, when I would run, let's say, YugabyteDB just on bare metal on my Mac, it's usually faster than when I run YugabyteDB in Docker on Mac.
Yeah. Usually I start Docker containers, and even more than that, because I test replication. but it really looks like it is stuck.
You want to restart it? Let's restart it. Can you kill it? Does it allow you to kill it?
I can even restart Docker, and we will see what happens there. We will start everything, and maybe in the meantime, I will just search for a blog of mine.
If you want to fix it, I can. Yeah. If you want to fix it, I can show the guys that promised highlight about Con gateway and how we.
Let's do that, and then I will restart everything. Yeah.
Okay, but don't restart your laptop, otherwise we will.
Yeah.
All right, my friends. While Frank is fighting to his Docker environment, let me take over the stage because I just have one highlight that might be interesting for a few of you, especially if you. So, folks, some of you might already know Con. Con is the company that creates one of the fastest and most well-known API gateways and service meshes. So generally, when you have many microservices or many other applications, and you want those microservices applications to interact through gateways or service meshes, or you want to create an API service mesh for your and make it visible to third-party applications, you can use Con. So Con is like for that type of use cases. One of the fastest growing startup companies in this domain. And Con, what's interesting about Con is that it uses Postgres internally. So whenever you are generating you start this Con, right? And you have several microservices and you want to create several routes. For instance, you say that if someone sends this HTTP request, that this HTTP request needs to go to microservice A. If someone wants to post something to this REST endpoint, this request goes to microservice B. So like that's the most trivial example. And all that configuration about roads, different security policies, etc., is stored internally by Con in Postgres. So Con uses Postgres by default from day one. That's the primary database of Con, where it keeps all the metadata and configuration for the gateway and service mesh. And also historically, Con was like, and here is, for instance, that's what happens. I will share that article with you. I created an article on my DZone account where I showed how you can run Con on distributed PostgreSQL on YugabyteDB, because many customers of Con, and I work with the Con community as well, they deploy Con gateways and service meshes across several availability zones and regions and countries. And when they do this, they also want to scale Postgres, but the scaling of Postgres part is a little bit challenging. That's why many were asking, like, hey, can we just use YugabyteDB instead of Postgres when we deploy across multiple regions and zones? And generally, right now, it's possible with the latest version of YugabyteDB that Frank is showing you. So this is what, for instance, happens when you start Con gateway or service mesh on Postgres. Like you can connect to your Postgres and you will find that under the Con database, there are many tables that are used by Con internally. Like the list is very long. Con uses a lot of Postgres internal capabilities and features. And what you can do right now, this article shows you just when you're starting Con. So this is configuration for Con. That's how you start, for instance, Con gateway in your Docker environment. You keep using Con database Postgres implementation, and then you're just connecting to your YugabyteDB cluster. That's it. And then you will get that's a screenshot of my locally running 3-node YugabyteDB cluster. And right now Con uses YugabyteDB. Historically, because we started working with the Con team a long time ago, but there was some DDL feature that were not supported by YugabyteDB yet for our distributed storage environment. And eventually we supported it, and right now it works. But another question that some of you might ask, so like it works right now. That's the beauty of the Postgres compatibility that we have. However, like why Con has this configuration, Con database Postgres? Does it mean that Con supports other database backends for its internal metadata and configuration? It still supports Cassandra. So historically, Con supported both Cassandra and Postgres, but then they discontinued Cassandra officially like a year ago. Cassandra exactly was used by the Con community for distributed deployments, like multi-zone, multi-region, etc. But then the Con company decided, no, folks, we don't have time, we don't want to have resources, let's say, just to support two different databases, Postgres and Cassandra, and they made a bet on Postgres. So right now they only officially support Postgres, and that was the right bet, because right now, like, they use Postgres, and if anybody wants to have API gateway service mesh across multiple distant locations, people can use YugabyteDB, because we are Postgres that scales and never fails. All right, so that's a quick intro that might be interesting for some of you who are working with the APIs and service meshes, and I will share the link to this article in the comments. If you have any questions right now, let's get them answered. So let me see. Do you have any questions? Yeah.
Yeah, if there are questions. If not, I have my environment that is working again.
All right.
Finally, I started a Yugabyte cluster in another VM that I have in the cloud. Let me put that. Okay, and then, yeah, because Docker was not restarting. Yeah, no, Docker is restarted, but I have an environment in the cloud, and that will work much better. I have created the table that I wanted to create with the same number of rows. And I've also created a temporary table, but I will show that later. So basically, I have my demo table here. And I will run directly an explain, analyze. So in Postgres, explain shows the execution plan, and you have multiple options. If you just explain, it will parse the query planner will establish the plan and just show it to you. But usually you want to run the query. If you want to run the query and get the statistic from the execution, you do an explain analyze. And so in Postgres, you do an explain analyze, and then you have already some information with the actual time. The cost, I remove it just because it's too wide for the screen. And in Postgres, you can ask for additional information, which is buffer. And it's not by default, but many people are advocating to get that by default. It gives more information about the work that is done, the reads and the writes in Postgres. And here I'm on Yugabyte. I'm running that with buffers, and I have what comes from the analyze, the actual time that it takes, the actual number of rows that was read, but I have nothing about the buffers. And that's simply because we have a different architecture where we don't read from the shared buffers, because that's monolithic. You cannot share buffers between multiple nodes. And then we cannot show anything about buffers. But before showing more metrics that we have some cases where buffers can be useful. And to show that, I will create a temporary table, exactly the same. So just create a select from it, and I run the same explain on the temporary table. And here I have the buffers information, so the number of reads and writes that happened. So for a select, there are even some writes depend on how it works. So first thing, I said that in Yugabyte we don't have shared buffers, and then how can I see statistics about the buffers? And the thing is that this is a temporary table, and for temporary table we use exactly the same as Postgres, because they do not need to be distributed. A temporary table is visible only by my session. So it writes only on the node where I'm connected, and then it reads buffers because it really uses the Postgres code. So this is why usually with buffers, you don't see a lot on Yugabyte. except for temporary tables. But usually we
I
are
got
not
it.
so interested by temporary tables.
So does it mean that we don't make temporary tables distributed at all, and we just reuse the Postgres implementation as is?
Yeah, for the moment, that's what we do. But there are some limitations. Maybe at some point we will use the same structure. I mean, we don't need to have them distributed. We don't need to have them resilient also, because if you lose your session, then you lose the data. But maybe it can be interesting to use the same LSM tree storage, even if it's not duplicated. But for the moment, we really use the Postgres code like that. So it creates the temporary table on the node where we are connected. So
Okay.
if
And
we
Frank,
want,
let me quickly pause you for a second. I just want to highlight that we've got a very interesting question from YouTube, from the DB Explorer. It's about how to select the best cloud native database like Postgres, Aurora, or CockroachDB. And we will answer this question, but a little bit closer to the end once Frank finishes his demo. So just in case we saw this question, thanks for asking it, and we'll get it answered a little bit later.
we keep that in mind. Yeah. So basically, if I just explain buffers on a Yugabyte table, so demo is a distributed table, I have no additional information because I don't read anything from buffers, but I still need more information about the reads and writes that are done. And this is where we have added another option that is dist for distributed. And this adds more information about the communication between the SQL layer and the storage layer. If I come back to the diagram that I have here, the dist thing is showing what we have there between the two layers. So here, when I'm doing a sequential scan on demo, so reading the whole table, reading how many? 1 million rows, I'm doing nearly 1,000 of read requests. And the reason for that is it could be only one, but we don't want to fetch 1,000 rows at the same time. So we have a parameter, fetch row limit, and I think we fetch by 1,000, 1,000 to 200, 1,024. So those are the number of read requests from between the two layers.
Okay, so it's basically let's say so right now you are running this in a single node configuration, right? Which means that you have one process of the Postgres
but
backend.
I still have the two layers, even if it's a single node. Yeah.
I mean, like those requests go over the network, right? You have this request over the network.
Actually,
but as long as you're
let me go back to the diagram, because it's not really going all to the network, because it's between the two layers. And then if they touch multiple tablets, they can be remote calls, but not necessary. For example, you can see only one read where it reads from multiple tablets. This is really, in the architecture, this is really between YSQL, the Postgres layer, and DocDB, the storage layer.
And so before
even reading for doing remote calls.
So what I wanted really to highlight, it's right now you have single node instance, right, in your Docker environment.
Yeah.
Which means that
sorry, but but I'm not on Docker here. Let me just check. I set up a free node cluster, I think. Select star from YB servers.
Okay.
Yeah, I started a free node cluster there.
So basically,
that explains those read requests. It's a sequential scan, so it reads from all nodes, but in multiple ones. Yeah. If let me do something, maybe if I limit that to less than 1000 or maybe 1000. So the one is there. So here I'm reading 1000 rows, and that's only one read request. If I read, let's say 1001, I have two read requests because the limit is 1024.
Question,
But
yeah,
yeah, what
question for
I
you.
wanted, just what I wanted to show here is that when I read 1000 rows from a table that is assured, it may read from multiple tablets, but it's still one read request.
And that's actually what I wanted to ask. Like, say from the SQL layer, so this piece, your terminal is connected to one of the nodes SQL layer to Postgres, and then when you want to read those 1000 rows, Postgres layer does one request to the storage layer, but effectively that request to the storage layer can be physically request to multiple tablets, right? It can be more than one. It's like one request between the query layer and the storage layer, but on the storage layer there might be more requests because the storage layer needs to pull data from.
Yeah, and this is where we have another metric that we added recently. So in this latest version, and that we show with debug.
Okay. Now
I
we are
think it's
talking.
called debug because the names are more internal. And here we see RocksDB metrics.
Mm-hmm.
So if I come back to my diagram, when it goes to the storage layer, it will read from one or multiple tablets. And the physical storage of those tablets is a LSM tree where we use RocksDB. The code is based on RocksDB with a lot of improvements, but basically we get the RocksDB metrics on them. And this is what I have there. And this is how I know that this has read from only one tablet because I have a seek only on one. So
Can you what happens, like, can you just request all the rows? Let's see how
so
this
without
information.
the limit,
Mm-hmm.
without
Okay,
the
yeah,
limit.
now you see.
So it was split. It was split because of the fetch size, and then each one has reached one tablet, and that to seek to a specific point. Maybe what I can test with no idea if it works because there are maybe some other parameters. This is the fetch size. If I set it to something higher, like I will try 1 million. I have no idea if it will work because that's a bit large.
Oh, yeah.
Cool. So here
Yeah.
I've set my fetch size so that in only one read request, I could read 1 million rows. But I still have 3 read requests because they are from multiple tablets. So maybe I was not 100% right when I was saying that those are the calls. Actually, those include the remote calls. But there are some cases, especially when it is run in parallel, where it doesn't really match the remote calls. But here you see that for each tablet, it was a different read request, even if everything can fit in one.
That's good. That honestly, this makes things clearer. But let's say that, and I think that when you were doing this request with the limit, that request went just to one single tablet, I guess. If just
Yeah, because
that's
1000. Yeah, basically the hashing. I have 3 tablets, so I have 1/3 of the rows there. So if I read less than 1/3 of the rows, it will read from one tablet. Because if I run with a limit, there is no reason to touch multiple rows if I can just read one.
Okay, makes sense. So, folks, if you have any questions about this, just feel free to ask, and Frank will be able to demonstrate it. Because there are many details. Seek and RocksDB seek. What's
So there are many
what does it mean?
details, and maybe you don't need all of them, and that's probably why it's behind the debug. It's really, we want more information, but we don't know if we need all information. The most important for me are the seek and the next. LSM tree is a sorted structure, but like with many index, like with many files, when you want to access to something in a file, you usually go to a specific offset and then you read from there. That's typical of random reads or even sequential read when you want to read from a range. So usually in any structure, you have to go to a start and then you read from there. And it's probably more expensive in most of structure to go to a specific offset for different reasons. If it's a disk, maybe there is some latency. Here, the reason is that the LSM tree is sorted on the keys, and then to go to a specific place, it needs to compare the keys. So there is some CPU usage to compare the keys and to go to a specific place, a specific range, the start of a range in the LSM tree. And also because you seek to a place where you were not reading just before, there are more chances or less chances to find it in the cache. So the seek is some CPU and maybe some IO because you are really doing some random reads somewhere. And then, so here, the minimum that you can do, because you have three tablets and you want to read with a very large fetch size, so the minimum that you can do is go at the beginning of each tablet, and those are those 6. The 6 go to the beginning. I just know that because it's a sequential scan without any condition. So it starts at the beginning and it will read to the end. So it starts at the beginning. So one for each tablet, and then it reads the next rows. And that's less expensive because reading the next rows is just going to the next one. So probably it's already in cache, and you don't have to compare the key. You just follow to go to the next one.
How will this execution plan change if you add order by to the request?
Yeah, good question.
By the ID, like by the primary key, order by.
I think it's ID. We will see. So
it's the same.
What do we see? So we have the same, and because the same is fetched from the different tablets, and the order will happen only on the SQL layer. For example, if I show, because I have hash sharded there.
But on the storage layer, nevertheless, on the storage layer, it's already sorted, right? On every tablet. If you take every tablet individually, everything is sorted, right? Because that's LSM
no,
tree.
because it's hashed, so there is the YB hash code. In theory, but I don't think we push down this. In theory, if I order by YB hash code of ID and then ID, in theory, this comes already sorted, but I don't think we push down that. So we do not use that because it's still a sequential scan.
Yeah, just sort.
And you see, because I mentioned buffers, the one that is more useful on Postgres than on Yugabyte, but because I mentioned buffers, I see the buffers used for the temporary, because we still use Postgres buffers for the temporary tables, but also the sort has to write to an internal temporary table. So buffers may still be interesting information if you have sorts, for example.
But could you please also do this? Let's select all the rows from this demo table that are bigger than I don't know, 50,000.
Let me.
That one,
Yeah, maybe I will start with an equality, because that was. Oh, let me check. I will keep the fetch size that is very large. We will see. And so first I will do an equality. So the ID equal 42 there. And here I didn't mention debug and dist debug. And we will get all metrics for a point query. Here we read only one row and we know exactly where it is because we have the hash value and it's the ID. So that's an index scan on the primary key that gets directly to the right place with an ID. So that's the SQL level of what happens. Between the layers, that's one read request, because we know exactly where we go. We don't have to go to 3 tablets like a sequential scan. We know exactly which tablet holds the hash value for this one. And then within that tablet, that LSM tree, we can directly seek to the right key. So to the ID 42 in it, one seek and one next to read the row.
And when we seek, right, we take this ID, we calculate the hash code for this ID also, right? And then in the LSM tree, we will find, using seek, we will jump to that position in the LSM tree, and then we will do the read. Okay.
So it calculates the hash code from the value. And with the hash code, first it knows on which tablet to go, because the tablets are ranges of hash codes. So this is why it needs to read only one tablet, one read request, one seek, and then reading one row there. And if I do an inequality now, so let me run the same with ID less than 42. I'm back to a sequential scan. And the reason is that with a hash code, we cannot compare. That's with hash sharding, we are good to go directly to a value, but not for a range. So this is a sequential scan. It reads 41 rows, so the 41 below 42. In one read request, yeah, and this one explains what I tried to explain before. Let's look first at the debug matrix, the 6. So it was a sequential scan. It had to go to 3 tablets because basically it has to read everything. It will read everything. The filter is pushed down, but still on each LSM tree, you need to read all rows and then apply that. So this is why you see 3, 6 going to the beginning of each tablet and then reading all rows there. So it goes to the 3 tablets, read all rows, and then filter to return only that. But the difference, I will run again the one that was a sequential scan without a condition. The difference is that when I had a condition, I had only one read request. Without the condition, I had 3 read requests. But those are still sequential scan. They still read the same number of rows. And it's not because of the fetch size, because I've set the fetch size to have everything there. The difference is that here, I still read from 3 tablets, but in parallel.
Okay.
If I come back to the schema, the idea is that here, in one case, I read from 3 tablets, one after the other. Then I send 3 read requests, one for this, one for this, one for this. For the other one, I have only one read request, but it will, in parallel, read from the 3 tablets. And do you know why we do that parallelism. In this case, where we have a filter, and not in this case where we have no filter, because maybe you want to scan all rows in parallel. And that also comes from the architecture. If we read 1 million rows from many tablets because we have no condition, then we have to fetch all those rows in this single process, because the Postgres backend is a single process. And it makes no sense to read in parallel a lot of rows that finally will have to be processed, filtered, ordered, whatever, by a single process. It's interesting to parallelize an operation only if you can parallelize in all layers. So basically, if we full scan, we know that we will read all rows, and anyway, we will have to process all rows in the SQL layer. So makes no sense to overload all the tablet servers. But when we have
because here
a
is
filter, we know that we don't have a lot of rows. So there, it makes sense that 3 tablet servers do the read in parallel, filter in parallel, and then the Postgres backend will get only 41 rows, and that's okay.
So what we need to do, let's say, is to add this information that something is being done in parallel. Because Postgres actually does this. Postgres, when sometimes you see that they add those worker nodes, like something related to the workers. That means that they spin up several workers, and the job and that query is being executed in parallel. That's what we also need to add.
Yeah, but I think we have also some colleagues working on that, the same parallelism, because we can have both. In some cases, we want to be in parallel on the tablet server. For example, this case where I read 1 million rows to finally return 41. I want this read to be in parallel, but I don't need multiple threads to process 41 rows. In this case, then probably I want to read in parallel from multiple ones, but also have multiple Postgres backends to process them. And this is where we can use the Postgres parallelism, the 2 levels of them. We can parallelize the SQL layer, and we can parallelize the DocDB layer. So we will have that, but for the parallelism in DocDB, I think that what we could do is having one more metric there, telling that the read request was split to was parallelized or not. For example, it could be interesting here to know that we have 1 read request, but behind 3 remote calls, because obviously, because it is distributed by hash, probably those 41 rows are from different tablets, and it had to go to the 3 tablets to get them. So could be interesting to see the number of remote calls. I just guess it from the number of seek, because a sequential scan has no reason to seek multiple times in a single tablet, in a single call. So probably there were 3 parallel calls there.
All right, wonderful. Anything else? You have 2 minutes left if you would like to demo anything else, and then we will switch to the questions.
Yeah, maybe you can switch to the question. What I think can be interesting to do is to do the same with a range primary key rather than hash.
Okay, then let's do this. Let's answer the question, and then we will finish with the range key, because that's also was one of my follow-up questions, like follow-up asks for you. Just let's show like what happens.
I changed my primary key, so I dropped the old one. I create a new one ascending with a ask, and while this is running, maybe we can answer the other question, and if we have time, we come back to it.
Yep. All right. So let's get back to our original question by the DB Explorer. The first one, it's a 2-part question. The first one is how one should choose an OLTP database for cloud-native applications on AWS. Say Aurora, Postgres versus CockroachDB versus YugabyteDB. So look, this way, it depends on your scalability, high availability, requirements and latency requirements, because every database, because apart from Aurora, apart from YugabyteDB, you also on Amazon you have AWS RDS that runs just a standalone Postgres instance for you, right? Or you can just go to AWS, you can spin up that EC2 machine and you can run Postgres all by yourself. There are many different options. So primarily when you select open source Postgres on AWS or Aurora or YugabyteDB on RDS, you need to think about your scalability and high availability and performance requirements. Why? Because if you take, let's say, Aurora as an example, architecturally, Aurora comes with one single master instance, primary instance that scales, that handles both read and write requests. And then if you want, when we're talking about Aurora scalability, it means usually for read requests. So like Aurora allows you to attach several read replica nodes in different locations so that you can scale read requests for your client applications. If this is enough for you, and Aurora is designed primarily for like single region deployment, there is a notion of the global Aurora, but for the global Aurora deployment, you need to have standalone Aurora clusters with asynchronous replication. It might work for you, it might not work for you. So generally, if you just want to, if your availability, it's all about you want to tolerate zone level outages, and you just you are okay to have one single primary instance of the database that handles reads and writes. And if that instance goes down, you're ready to wait for several minutes for your application and database to come back to operations, then probably you can go with Aurora. When it comes to YugabyteDB, with YugabyteDB, it scales both reads and writes, meaning that you have every node in YugabyteDB is a primary, meaning that the data is sharded, and one node is responsible for one data subset, another one is responsible for another data subset, which means that your client application is scaling both reads and writes. From the high availability perspective, you can deploy it across multiple regions, you can deploy it across multiple availability zones, and etc. And you can achieve region level tolerance, high availability. Even if a region goes down, you will be okay with your YugabyteDB cluster, because during those outages, recovery time objective is like measured in seconds. And Franck actually created a wonderful blog post explaining how it works internally. And there are many other parameters.
It's resilience. It's more than availability in the sense of Aurora. The availability is still a failover. It's fast, but it's still a failover, which means that all connections are down and then reconnected to another one. Even if you use a serverless Aurora and it needs to scale up, at some point it has to stop an instance and restart one. With YugabyteDB, it's more than that, because it's resilience. When a node is down, the others just continue. They don't even have to fail over. They just continue. In behind, there is a new leader that is elected, but nothing fails. Even the transaction, the current transaction is not rolled back. It will just continue with the new leaders.
Mm-hmm. Yeah, so hopefully it answers your question. Like, even if you compare Aurora, is there a single master architecture that can scale reads, and primarily you use it with a single region deployment?
But there is also something in the Postgres compatibility. Of course, Aurora has a better Postgres compatibility, because when you run, even if it's a fork on a single node cluster, so it's much easier to use all features as is. So basically, Aurora is the same as Postgres, the same behavior as Postgres. With Yugabyte, there are still a few features that we have to implement to behave the same as Postgres. And Cockroach has much less features because they don't reuse. It's not a fork of Postgres. They just implemented feature with the same protocol and syntax. So between those, there is also the Postgres compatibility that changes.
That matters a lot, because let's say from the storage, from the distribution perspective, YugabyteDB is quite comparable to Cockroach. But what makes us different is that YugabyteDB is open source, fully open source, same as Postgres. We are fully open source. Cockroach is not fully open source. And lately, YugabyteDB belongs to the Postgres family, because we are built on Postgres. We are Postgres that scales and never fails. Cockroach is moving in a different direction. It's adding, feature by feature, incrementally, gradually, over the time. But that's a much, much longer journey.
And the second part of the question was why Yugabyte not suites for all app use. Mostly because I think there are two things. One thing is that maybe for OLAP you don't need ACID transactions, so you have also other solution. Yugabyte distributes without any compromise on consistency on ACID transaction. For OLAP, maybe you don't use, so you have other choices. And for the moment, we have more optimization for OLTP than for OLAP. That will come. We are adding more and more push downs. So the pushing the aggregation, the analytics, the sort to be run in parallel in DocDB in the tablet server. But there are some OLAP use cases where we may not have the same optimizations as other solutions that are not ACID, are not consistent, but are okay for some analytics.
Exactly. I mean, like when someone usually asks me, like, why are you suitable for a lab? I usually say, like, we are suitable for a lab to the extent you would use Postgres for their lab, which means
Yeah.
that, I mean, all lab systems and OLTP systems are different. For OLTP, usually you have a predefined set of queries that your application is going to send to your database, and you design your schema and you create indexes. You just use explain to understand the access patterns. You optimize everything for a predefined list of queries most of the time. At least you can figure out. In OLAP, there are no any rules. It's just like Wild West. You have this data, and one user can send this request, another that one, and like those who requests are fat, like the big one, which means that you deal with different use case, and you even on the storage layer you arrange data differently. Like many OLAP systems, they are columnar by
Columnar.
default, meaning they're columnar. It's just different format.
Because you
And
cannot predefine the right indexes because you don't know the query. So you store everything columnar, so that the filters on the column can be done later. But being columnar is good for OLAP, but not very good for OLTP. So because you
yeah,
have to
so
lock
my
many structures. Yeah.
so here is I usually support, one of the mantra of Amazon AWS. They usually say that they create those purpose-built solutions and databases. Like YugabyteDB and Postgres were purposefully built for LTP systems. Yes, you can run some complex analytical requests over YugabyteDB and Postgres, etc. But you usually don't use those databases as OLAP systems, because for OLAP there are other purpose-built systems. Take Apache Pinot, take like Redshift, etc. There are many use cases. And then let's say if you're building this application, you need both OLAP and OLTP. You can use those systems, separately. If you want to run some federated queries across those systems, you can use Trino, you can use some others, technologies like Databricks. They can connect to different stuff and they can pull data for you from OLTP and from OLAP. It's all possible.
And for OLAP, usually you don't need it to be real time, so you can accept asynchronous replication, and then it's easier to use another database. For the analytic queries that you find in OLTP application, you want them to run on the current version, so you want them to run on the same database. But for OLAP, probably you accept a lag and replicate asynchronously to a columnar storage.
Yeah. So hope this answers your question, my dear friend. If not, we can continue our conversation in Slack, or we can always discuss it later. So Frank, we are running out of time. So you want to show us the ranking index, or?
Quickly, I've just changed the primary key. So if I look at it, I have it. Of course, I can still run with an equality, and I have a lot more metrics there. I can run with an equality. I have an index scan, and that sticks directly to the right place. I have even more information about the cache. You probably don't need all that except for troubleshooting specific cases. This is why it is behind debug. But the thing is that if I run a query to see the rows below 42, now that I'm range sharded, this can go directly to the beginning of the range. So stick to one place and then read the others. And I can also show something very quickly. Let me add an order by to it. So it's basically the same, because when you read from an index that is range ordered, the rows come in the order. So the seek and the next come in the order. But if I rent a descending order, and that's a difference with Postgres. In Postgres, with B-trees, one way or the other way are the same. Here in a LSM tree, going ascending in the same order as the index is faster. Here we have a scan backwards, so it's just reading the rows in a different order, and you can see many seeks, same number of next. I'm reading the same number of rows, but it's really like, instead of going to the previous one, so you see the previous, it goes to the previous, but then has to go to the next. And sometimes when comparing the key, it has to go to one place and then to another. So yeah, those metrics also help to understand why a scan backward may take some more time when compared to a scan forward. Without the metrics, you can only look at the time, but the time depends on many other things like the cache, everything. So those metrics are really useful to understand the complexity of the access pattern behind. Okay. Did I lose the network?
All right.
Did I lose the network?
Let's say good, because it feels like,
I don't know.
no, I think that might have happened on my end or on your end as
Okay,
well,
perfect.
because I don't know, like, because we are both streaming from hotels in different part of the world. But hopefully, folks, those who are watching us, you saw the final explainer by Franck without any issues and without any delays. So, generally speaking, thanks a lot for joining us today. And Franck, you want to say something else before we end the stream?
And questions, welcome on Slack, on whatever channel. If you have an explain plan, I love to look at execution plan. So if you have an explain plan and want to understand some metrics, just ask on Slack. That's the easiest. Yeah.
Wonderful. Thanks a lot. Thanks a lot for your demo today. Thanks a lot for demonstrating us this new additions and metrics for the explain. It's certainly helpful, and that allows also to learn insights and internals of YugabyteDB. So folks, have fun building distributed applications on YugabyteDB, and we'll see you in a couple of weeks during our next Open Hours stream. Bye-bye now.
Bye.